All right, we're all set. You want to?
All right. Hey, let's start off. We'll probably get an influx of people here at 9 o'clock that either didn't see or forgot that this had an earlier start. So our guest this morning, Tim LaPara from the University of Minnesota, has to join us a little bit early as a class to teach at 9:30. So we're going to get a little bit earlier start. Tim, it's great to have you with us this morning. Tim joins us from the Department of, see if I get this right, Civil Engineering, Civil, Environmental, and Geoengineering at the University of Minnesota. Do I have that right, Tim?
Yeah, you do, and I'm sorry for the complications.
Yeah, no, that's fine, and I think we're all set and ready to go. Tim has done an enormous amount of work on microbiology pertaining to wastewater and to drinking water systems. And this morning, he's going to talk to us about some really interesting work, I think, on the SARS CoV-2 virus in Minnesota's drinking water and subjects that pertain to it, including vulnerabilities in our drinking water system. With that, Tim, I'm going to let you take off and run with it. Thanks a lot for being able to join us and tell us about this interesting work this morning.
All right. Thank you, Mark. Thank you for the invitation. Thank you for the opportunity to speak today. So, yeah, this is basically, I guess I'll summarize it. This is early work. That we've been doing, well, I'll give you a timeline so you can sort of see the full story. So there we go. So let's talk a little bit about SARS CoV-2. It basically, as all of us know all too well, leads to what we'd call severe acute respiratory syndrome. It's caused by a coronavirus. And as I'll show you pretty quickly, it's genetically linked or related to the same virus that caused the SARS outbreak of 2003 and the MERS outbreak of 2012. And so here's sort of the schematic of sort of the evolution of this virus. And its origin is unknown. Its origin is of some political controversy. But this is sort of a full virome phylogeny. And so what you can see, I'm hoping you guys can see my arrow, but the red, or excuse me, I can get my colors mixed up. Most of what we have up here in the very part of this is the original SARS virus. Then we have a bunch of bat-related viruses that have been found. Here's a handful of other viruses, and this is sort of a phylogenetic tree. So if you sort of turn it on its side, it's somewhat like a family tree. We see the MERS virus down here. Here's all of the SARS CoV-2. These are different, basically variants of the critter that's making all of our lives such a challenge right now. And then, one of the questions is, where does this thing come from? And so basically what we have now at this point is its closest relative, and it's, somewhat distant, is other bat coronaviruses. I'm not even sure how to pronounce this animal, pangolin, is my guess. It's in common language, that's an anteater. This virus has been found in those organisms, but we don't know if it's necessarily a legitimate host for the virus, rather than it's just something that got infected. So anyways, the origins of this thing is a little bit different. It's unknown, and that's obviously complicated so much of our lives for the last year. The virus structure itself, basically it has 6 functional reading frames. It's got 2 replicases, it's got a spike, an envelope, a membrane, and a neocapsid. So just a couple little tidbits off of this, why I'm including this slide. They're called enveloped viruses because there's an envelope around the genetic material. You might jump to the conclusion that makes the virus more resistant to treatment, but actually it's the opposite is true. Enveloped viruses, as I'll show you, tend to be pretty susceptible to treatment. I've got a asterisk by the spike protein. The spike protein is pretty important for a handful of reasons. One is that's the thing that seems to have evolved the most from, I guess, this previous slide. And so that ends up being an important target for a number of things, up to and including the vaccines that we're hearing about. Both of the two vaccines that are likely to be approved by the FDA this week are actually variants of the spike protein, and so that is important for infectivity, and so obviously it's also important for our immunology as well. I don't know. Oops, maybe I just did something wrong. Okay. There was something. I sort of decided to go through a timeline, somewhat personal, somewhat from the literature, and it actually ended up kind of telling an interesting story as I was putting together these slides. So literally a year and 2 days ago was the first recorded case in Wuhan. Things got out of control pretty quickly from there. I know there's some evidence that the virus has actually predates that, but the first recorded case in Wuhan was about a year ago. Within a month, the Chinese government had announced that they had identified the virus causing the outbreak. That was through sort of shotgun DNA sequence or DNA/RNA sequencing. Within a couple weeks, they had confirmed that human-to-human spread was happening and obviously very prevalent. By mid-February, the virus was officially named SARS CoV-2, and the disease was named COVID-19 by the WHO. Here's the personal thing. I took my son to a Gopher baseball game at US Bank Stadium where they won 5-3. That was on March 10th. A reasonably normal night in my life. The next day, things went a little crazy. The WHO officially declared COVID-19 a global pandemic. The U of M canceled all in-person classes, initially just for a month, I think, and then eventually for the entire semester, and that's obviously continued. Also, kind of around the same time, the SARS CoV-2 virus was detected in sewage, and we started noticing that it was showing up in fecal samples as well. So here's a paper. It's not literally the first, but it was one of the first. I'm sort of showing you this for a couple of reasons. First of all, I know a number of these people personally. Kyle Bibby, who looks like about the fourth author on this, I would consider a friend. I've taken him fishing. And his postdoc, Aaron Bivens, is on there, who also likes fishing, but I haven't yet had the opportunity to do that with him. Warish Ahmed is somebody, a really good scientist from Australia. And so anyways, they published this in mid-April. The thing I would like to point out, and so I've sort of pulled it off of here, things went a little wonky with the science there for a bit. This manuscript was received on April 14th, 2020, and they accepted it in revised form the next day. So I don't think this thing received the rigorous peer review that we would like to expect. But I will tell you that I actually find the work to be pretty good, but it just didn't go through the peer review process the way it normally works. So continuing on with the timeline, literally the same day this manuscript was received by the publishers, a handful of state legislators reached out to me and Ray Haselski, having heard that this virus was found in fecal material and in sewage, and expressed concerns that would end up in our drinking water. We went back and forth with the legislators, talking about how, based on what we know of our drinking water infrastructure and organisms in the environment, why this may or may not be of concern. But within 16 days of that happening, Governor Walz was signing over approval for us to investigate SARS-CoV-2 in drinking water. I will tell you, kind of about this time, there was a strategic decision made by Ray and I, knowing that a number of people were actively looking for this virus in sewage. And the reason for that is people have now shown that the levels of this virus in sewage parallels quite nicely the number of cases in the community. And so it becomes a way to, what do they call it, wastewater-based epidemiology. So you can track the spread of the illness based on sewage rather than on patient data. So there's some advantages to that. So anyways, Governor Walz signed us over. We got our official start date on May 14th. May 13th, we're collecting our first samples. And then we did this for about 6 weeks. And so the samples that we're going to show you data on are from May 13th to June 24th of 2020. So what did we know about this virus? The problem is it's pretty new. This is a manuscript that was published in 2020. I'll again point out that this one was submitted for publication on March 20th, and it was accepted for publication on April 27th. One might wonder how you write a scoping review of a virus that we know virtually nothing about before we learn anything about it. But, you know, academics like to publish papers, I guess. So I've boxed part of this abstract, and it's pretty useful. So the coronaviruses in general seem to have low stability in the environment, and they're very sensitive to oxidants like chlorine. They are inactivated significantly faster in water than non-enveloped human enteric viruses. So that's good. Again, I said the envelope viruses, you might think that gives them better protection, and in fact, the opposite is true. Temperature, of course, is a very important factor for survival, like virtually every other living creature. And this is one's interesting. There's no current evidence that human coronaviruses are present in surface or groundwaters or are transmitted through contaminated drinking water. Yeah, there's no evidence of that because I can't imagine many people had looked for this by March. And then, of course, we need further research. So this is sort of a review or a prediction, depending on your perspective on how to interpret that paper. Okay, so I just kind of want to summarize where we were, because I think it's important, because a lot of people like to look back in time with this virus and say, oh, you made a mistake. And, you know, I think we need to be a little empathetic as far as what the situation was and what we knew or didn't know, and being logical, making educated guesses or just flat out guesses as to how to go forward. So the situation we faced is we had a novel, highly contagious and deadly virus. We knew the virus was shed with feces, suggesting that there could be concern of the fecal-oral route of infection. Clearly, there's highly contentious politics, both locally, at the state level, at the federal level, and even internationally, of course. Further adding to our complications, the university banned undergraduate research, undergraduate students from working in the laboratory for their own safety, and simultaneously, we were not allowed to hire any new personnel to do this work. So we had a challenge. So what we ended up doing, and this made the project very expensive, especially when you look at the fact we only collected samples for 6 weeks. We had to, Professor Hozelski and I had to do two very unprofessor-like things, in that we had to get off our butts, get out of our offices, and we had to go collect these samples ourselves. So the thing I will tell you, or what I'm about to tell you, is the same thing we told the legislators at the time. We didn't want to bet every penny we'd ever earned in our entire careers, but we were pretty close to that. We felt that the drinking water infrastructure, in a conventional, traditional sense, would provide robust, almost complete, if not complete, protection against this virus. And I'm in this case, with this slide, we're talking about the source being surface water. So this is what would be the case in Minneapolis, St. Paul, St. Cloud, and a handful of other public water supplies throughout the state and obviously throughout the world. So basically, this is a schematic that I teach from. You know, coagulation, flocculation, sedimentation, filtration, those are designed to get rid of colloidal particles that otherwise you would have a somewhat difficult time physically separating. The particle sizes that those are designed to remove are in the order of 1 to 1,000 nanometers, which is right in the sweet spot of this virus. So those technologies should provide robust protection. And then, of course, by this time, we knew that envelope viruses were susceptible to disinfection. So you throw those treatment technologies followed by disinfection. And, you know, we've got, 100 years of this technology being demonstrated of completely thwarting the fecal-oral route of infection. And so we felt there's no chance. And the legislator said, well, please look. The other, that doesn't excuse me, the previous slide doesn't represent all of our drinking water infrastructure, and it's hard to do it in 3 slides, but I'm going to give it my best shot. An alternative would be a public water utility where the source is groundwater rather than a surface water. Sometimes there's treatment of this water. I have lived in Blaine for most of the last 20 years. Blaine basically will aerate their groundwater to remove iron and manganese. They then remove it by filtration. Some cities, public water supplies will perform water softening, but for the most part, you can take water out of the ground as a public water utility and basically just disinfect it and distribute it. And even if groundwater became contaminated with these viruses, I strongly feel that this would, just a simple disinfection of groundwater would provide robust protection. Okay, so we felt good about these two. You might say, well, gee, that's pretty much all of public water supplies. And that's mostly true, but it's certainly not true that it's all of where we get our drinking water. The bigger concern that we had, and this is what we told the legislator, was really sort of the weak spot in our drinking water system, not necessarily speaking infrastructure here as much, but just sort of where those are situations where we have groundwater that we use without treatment, meaning no disinfection. And this will occur in certainly homes that have their own private well, but it also occurs where we have public water supplies that routinely, reliably, always test negative for coliforms. There's a loophole in the legislation and regulations that allow these public water supplies to produce water, send it out to their communities without any treatment or disinfection whatsoever. Very much paralleling what you might have in with a private well in a home. So this is where we were somewhat concerned, and we thought this was going to be the more likely place where SARS CoV-2 could cause some issues. So this leads us to sort of our reconnaissance, and we're worried about the fecal oral route, and we have assays that do this, and there's a number of ways you can do it. The sort of traditional gold standard is the coliform assay. It's now been commercialized and made super easy to do. I'm showing you a slide for the IDEX ColAlert assay. It's a little expensive on materials, but it's super cheap when it comes to labor. So this is really common. Basically, they sell you a bottle, which I'm showing here on the left. It's sterile, it's sealed. You open it up, you collect your sample. It's got a little line. So it's a little smaller than my fist that measures out 100 milliliters. You throw in this little packet, shake it up, throw it in a tray, seal the tray. And if you want to look at coliforms, they turn yellow, and the size and all of these various different yellow, I don't know, I guess, growth chambers, mini growth chambers, indicate how many coliforms we have. If you hit it with UV light, you can also measure E. coli by this method, okay? So what we're saying is, or what I've been saying is, if public water supplies test completely negative for this, then they can be distributed without any disinfection. The thought being, if they're absent coliforms, which are indicative of fecal contamination, then the water is safe to drink. Sort of the new direction we're going with this is genetic testing of the drinking water. All creatures, all living creatures, and even all living creatures have RNA and DNA. Viruses aren't necessarily considered to be living. They'll contain either RNA or DNA, and we can quantify those by quantitative polymerase chain reaction, or PCR. So you've probably heard a lot about this in the sort of general public. They talk about, the gold standard PCR test for determining whether or not you actually are sick with SARS-CoV-2. So what they do is they do a nasal swab. They extract and purify RNA out of your nasal swab, convert it to DNA, and then quantify how much of the SARS-CoV-2 converted DNA, cDNA, is in your nose. And if it's there, you're positive. If it's not there, you're negative. We're literally using the same techniques. And what's great about these techniques is they can allow us to quantify pretty much anything we want, as long as there's a specific, or as long as there's a genetic target target can be specific, like, so for SARS-CoV-2, we actually target the nucleocapsid, the N target. There's other assays that are available, but we could quantify all bacteria. We can quantify a handful of different things. What's really great about these assays is they're very sensitive. They can allow detection down to as few as 5 RNA or DNA molecules. So if you think about this, I guess I remember I reviewed a paper from somebody who had invented a probe that you could stick into water and it would measure DNA levels for specific organisms down to like 10 to the minus 12 molar. And they're like, this is incredibly sensitive. I don't know, is that picomolar, femtomolar, crazy low levels. But when we're talking 5 or molecules, we're now talking 10 to the minus 23 molar. So improve that detection by another 10 orders of magnitude. And that's kind of where we are with these assays. So it's really quite powerful stuff. Here's just a list of the various genetic targets that we've used looking for specific pathogens in drinking water in the past. We kind of end up looking for the same critters that you might think of. This list is a little bit longer than normal. We've got a bunch of fecal oral route enteric pathogens like Campylobacter and E. coli and Shigella, Enterococcus, adenovirus is a virus. We also throw in all bacteria, but we can even look for opportunistic pathogens such as Legionella or Mycobacteria. So it's a pretty powerful technique in general. And it's also been very useful. So this is work published 8 years ago by my friend Mark Borchardt out of the USDA lab. What he's been doing, really, to be honest with you, is challenging this notion that the fecal coliform assay is a good metric for the presence of fecal pollution. So this is work he did in some small towns in Wisconsin, where they collected water samples. The overwhelming majority, if not all of these samples, tested negative for coliforms, but he was able to quantify specific viruses in the water. So if you look at this data, and I realize it's small, like he's got an all virus, norovirus of the specific type on here, adenoviruses, enteroviruses. And basically what he did and what is shown in this slide is he was able to correlate the quantity of viruses in the water with people actually getting sick. So AGI incidence is acute gastrointestinal incident, which he defined as 3 consecutive episodes of diarrhea or 1 episode of vomiting. Okay, so going to these fancier genetic techniques has substantial advantages for assessing the safety of our drinking water, provided beyond the sort of fecal coliform assay. He's since continued this work in the state of Minnesota. So you see a couple of these here. This is sort of a big summary of their entire paper. This paper was published earlier this year. They had a couple other nice studies. They've actually found Cryptosporidia and Giardia in groundwater in Minnesota as well. This is actually the paper on the right here is one of my favorite papers I've ever read. Basically, what they did is they analyzed and showed that negative pressure events led to continued contamination of the distribution system, demonstrating that maintaining a low-level residual disinfectant is very important for protecting public health. The one on the left I'm showing you just because there were avian influenza outbreaks in the last 5 years, and in addition to finding these human enteric viruses, we're finding other viruses in water. And so Mark was able to find avian influenza in groundwater as well. So from all of this is part of what motivated our concern to think that we might find SARS-CoV-2 in groundwater. Okay, so we found a bunch of other enteric viruses in groundwater. Why wouldn't SARS-CoV-2 end up there as well? So with all that, what were our project goals? We wanted to collect microbes using high volume water sampling. And I'll show you about that in just a moment. We wanted to look at surface water systems such as Minneapolis and St. Paul. Just to be clear, this water is exceptionally well treated. We expected them to be negative 100% of the time. We looked at disinfecting groundwater systems like Egan or Blaine. Those are examples. I will tell you, we did not trying to think. No, we did not collect a sample from Egan. It's just an example. And again, because this water is treated, we expected it to be negative. Then we also looked at the non-public and private groundwater systems, which we were concerned would be susceptible to contamination. Of course, we didn't know that, and we still don't know that. I guess I'll tell you that. So about these large volume samples, this is, again, so I mentioned Mark Borkart. He taught me how to do this. So you can purchase these kidney dialysis membranes. They have a surface area of 2.5 square meters, which makes them really effective for collecting and filtering water samples. The traditional filter that we use in the lab is 47 millimeters. If you can see me in the camera, $50 if people use those anymore. Bigger than a quarter, not particularly large. Those filters, in addition to having just a problem where they're fairly small, the other problem is you usually pull your samples through that filter using a vacuum. And so, atmospheric pressure is just under 15 pounds per square inch. That's not a lot of force. We can certainly push water a lot harder than we can pull air. So there's two major advantages to these. One is the increased surface area. The other one is our ability to push rather than pull. So none of the samples we did in this study were as large as 10,000 liters, which is what I'm showing here. We have collected samples as large as 10,000 liters. These are drinking water samples. Just to be clear, you can't achieve this with lake water. But with drinking water samples, we've done 36-hour sample collection events that led to 10,000 liters. Our goal in this study was about 1,000 liter for our sample volume. The limiting factor there became time. So each of these samples took about 3 hours of filtration to generate our samples. And then, so once we pushed our water through, the clean filtrate comes out. We then back flush the material off. We then concentrate the back flush solution. And basically what we do is we squish our sample volume of, let's say, 1,000 liters down to maybe 7 milliliters. And so we get a pretty substantial concentration factor. And that allows us, our effective sample volume on these samples is on the order of 100 liters, which is 3 orders of magnitude larger sample volume than the traditional coliform assay. So what we're doing here is our sample volume is 1,000 times larger, and we're doing genetic testing for specific pathogens rather than the sort of indicator organism that is fecal coliform. So we collected our samples. We then extracted purified DNA from that material that I showed you. We, for reasons that would be obvious to you if you joined us in the laboratory, we call that material snot. Mark has a fancier name for it. He calls it FCSV, final concentrated sample volume. We just call it snot because we're crude. And then once we do that, we then just quantify the target organisms by quantitative PCR and quantitative reverse transcriptase PCR if it's an RNA virus. Okay? So we were pretty well versed in all these techniques. Everything was great. So we just went out and collected our samples. We collected one sample from the surface water directly, basically Mississippi River water. I'm not sure if I'm allowed to tell you where we collected that sample, so I'll just go ahead and do it anyway, because we didn't find anything of concern. We collected that sample from the intake at Minneapolis Waterworks. We then collected 5 samples from sort of the public water that's treated and disinfected with surface water as the source. So those were Minneapolis and St. Paul out in the distribution system. We collected 16 samples from private wells. We collected 4 samples from public water systems that were disinfected, and the source was groundwater. We collected 4 samples from public water supplies that were not disinfected, that sort of loophole system. I know of a handful of public water supplies like that, and so we targeted those intentionally. And then I'm not going to show you this data, but just to be clear, and you'll get some flavor of this through this talk, our quality assurance, quality control measures were pretty stringent. We also collected 6 negative control or blank samples throughout all of this. I'm not going to show you those, but just trust me, they were clean. Most of our samples tested negative for coliform, so showing no traditional evidence of fecal contamination. There were some exceptions. One of our samples from private wells did have a low level of total coliforms, and 3 of our samples from those I'm calling them not disinfected because I don't know what a word, but from those public water supplies, 3 of our samples came up negative. The next thing I will tell you is that we tested a genetic marker that's kind of a newer one. It's called crassphage. It's basically it's a virus that we know very little about, but it infects bacteria that are in fecal pollution. So this is sort of a new fecal pollution indicator assay that people are pretty excited about. So it's a genetic indicator of fecal pollution. We didn't find any of that. Based on Borchart's work, we were also concerned about Cryptosporidium and Giardia. We tested for those. Those were also negative. I will tell you that all samples were positive for bacteria, which is my next slide. I put together this slide last night, reanalyzing our data. So I've sort of lumped our samples into 4 different bins. We've got the disinfected groundwater. We've got the not disinfected groundwater. And so you know, and I guess on the y-axis, so these are log of 16S rRNA genes per liter, which probably means almost nothing to you, but 16S rRNA genes are a measure of all bacteria in this assay. So if you think about, and then this is in log units. So what this is saying is we had about 10 to the 5 bacteria per liter in this disinfected groundwater system. It was a little bit higher, 10 to the 6 bacteria per liter in the not disinfected groundwater that were public supplies. The not disinfected groundwater that were private were a little bit higher. These are probably not statistically significant, just more variation. Again, so we had, I think, 15 of these and maybe 4 of these. And then the treated surface water systems like Minneapolis and St. Paul were on the order, I think it was about 5.5 log units per liter. Now, I've showed you, just to give you an idea, we've performed the same assay on tons of different samples. The strength of this assay is it's effective over 7 probably log units of biomass. So the blue line there is what we measured out of Lake Superior. If you've ever seen Lake Superior, it's some of the highest water quality, surface water quality in the world. You're talking Secchi depths well over 30, 40 feet. And so this is, this is drinking water. We'd expect it to be low in biomass, and sure enough, it is. The red line up there is what we measured out of the Mississippi River. So you get an idea. We're what, 1, 2, 3 to 4 to 5 orders of magnitude lower biomass in our drinking water compared to the Mississippi River, and a couple compared to Lake Superior. This is really important for QA/QC. This is consistent with what we've measured over, I don't know, probably 1,000 or 2,000 samples over the last 10 years. This makes us feel really good that our sample collection, concentration, and PCR are all giving us quantitative data for total DNA, or at least that leading to bacteria. So this is important QA/QC. So what I've shown you so far is we're negative for a lot of stuff and positive for bacteria. The reason why I'm going through all of that is because all of this is a lead in to tell you that so far of those 30 samples, all of them have been negative to SARS-CoV-2. So we found no evidence that this virus has gotten into our groundwater, at least last June, May time period. The other part of this QA/QC that's really important is we had to make sure that we could measure this from real world environmental samples. Quite a here, any one of them to get it working, but we were able to successfully quantify SARS-CoV-2 in the raw sewage samples from the Metropolitan Wastewater Treatment Plant in St. Paul at levels, quantitative levels similar to what had been reported in the literature at the time. So we feel really confident about our method. The one thing that was particularly tricky was, so when you extract and purify your RNA, that's tricky. We felt pretty good about that. But then the next step is you convert that RNA to DNA using what's called a reverse transcriptase enzyme. And it turns out that most of the commercially available reverse transcriptase are not designed to deal with environmental samples. That's important because environmental samples, whether it's sewage, soil, lake, river, it's a lot dirtier sample volume than, say, a nasal swab. And so what happens is you co-extract contaminants, and then those contaminants in your extraction inhibit that enzyme from functioning. And so we had to go through all of these steps to demonstrate that, and we can track a lot of it. We had to go through all these steps with all the QA/QC to make sure that our assay was working, and we're super confident that it was. The one thing I would tell you, I'm guessing there are folks here who have gone and gotten their nasal cavities swabbed and tested, and they came up negative, and then a couple days later they got sick, and then they went back and tested again, and they were positive. And so sometimes people will call that a false negative. Reality is it's probably in your nasal cavity. Off the internet yesterday. These are and of course we were collecting samples in here where the number of positive tests per day was on the order of tens to maybe a few hundred. And obviously now we've had this huge spike in SARS-CoV-2 levels. So our current plan is we're going to go out and collect samples and try to start measuring, see if we can find SARS-CoV-2 in our groundwater systems now. Certainly it's much more likely that we've got such greater numbers of infected individuals in our town, or in our state, excuse me. So with that, wrap up some conclusions. There's no evidence so far that we've got SARS-CoV-2 in our drinking water. We certainly wouldn't expect it to be in the overwhelming majority of our public water supplies because they're treated and disinfected. And, you know, we have 100+ years of knowing that those technologies are robust and exceptionally effective. And I often give talks on sort of science and policy, and certainly when I talk about politics versus science, I have this enormous bias that scientists and engineers are amazing, and we can do a lot of things, and you know, we can take us to the moon, and that's what I see, to go aerospace engineering, and then sometimes space shuttles blow up, unfortunately. So anyways, that's my bias. I'm arrogant about science and engineering. So anyways, we still remain concerned that we could find this virus in public and private drinking waters as long as there isn't any treatment. The problem here is we're trying to prove a negative, and the only way we can come up to any conclusion that's definitive is to actually find it. So it's tough to prove a negative, but we'll keep looking. So with that, acknowledgements, I have to acknowledge Ray Hazalski. I originally had his name on the title slide. Ray and I did the bulk of this work. So he's certainly co-author, first author, second author. We had complete joint duty on this. So I guess all opinions are mine. Anything positive that you like from this talk is his. Then his graduate student, Jiaoshen, did a lot of the sample processing. My postdoc, Chad Yu Kim, did the genetic analysis. Funding comes from the Legislative Citizens Commission on Minnesota Resources that allocated funds to us through the Minnesota Environment and Natural Resources Trust Fund, which you've seen here. And I will tell you that we are planning to, we have additional funding coming around this summer. So we're going to start this up again as well. And with that, I would love to entertain any questions if I can figure out with the technology how to, hopefully I can get some help.
Yeah, so thank you very much, Tim, for that great presentation. I do see one question in the chat so far. You guys go ahead and feel free to add more. There's been a bit of discussion around dose of virus and illness. Do you have any comments on that related to your work?
Not an informed comment. Yeah, I know a little bit of sort of about quantitative microbial risk assessment in general, and so there's usually a dose response curve that most people, that if you were to take a large number of people, the dose of the virus, the initial dose of the virus, and what fraction of people leads to an illness. I certainly don't have any knowledge of that as far as uh, what it would take to make somebody sick, and then in our case, if it's in water, would it make anybody sick? And to be clear, our concern really isn't about drinking water. If you're going to, the faucet, opening the tap and taking a drink, that's not our concern. It would be more respiratory related, so taking showers and things like that. But yeah, no, we're nowhere close to dose response curves in any way, to my knowledge.
Great. All right. Here's another one. Do you have any sense of the fate of COVID-19 in the environment? Is it similar to many other viruses in the sense that they don't exist long in surface waters?
Yeah, that's what we know so far. Warish, who I cited at the beginning, has done quite a bit of work on that. That's a lot of what he's been doing, and so that's true. The specific concern that we have is it seems that viruses are really nicely preserved under the conditions that groundwater has. So they do seem to stick around a lot longer in groundwater, and that's part of the reason why Mark Borchardt has been doing all this work. For whatever reason, viruses remain viable in groundwater for a long time. So that's our concern. But at this point, it's a qualitative concern, not a quantitative concern, meaning we need more research.
And then there's a follow-up question on that, that Minnesota wastewater treatment plants mostly stop disinfecting in October. Would you expect more COVID in the winter because of this?
That's a good question. I don't know where the virus is, what the fate of the virus would be through a wastewater treatment plant. I am a collaborator on a project that's scheduled to start this summer where we're going to look at the fate of envelope viruses through wastewater treatment. That work is led by Sebastian Behrens, but I'm the helper bee on that project. But so hopefully we'll find that out. My guess is I don't want to guess.
That's probably a good idea. We have another question. Says, I think I heard you mention something about looking at COVID in wastewater as a measure of its likely presence in community. Is there any focused work on that approach?
Yeah, there's a lot of focused work on that. There's a group of professors, a couple of professors at UMD who's doing that work. There are almost everybody who can do PCR, it seems like in the field of environmental engineering these days, is doing that type of work. What's been really frustrating to me that I've noticed over the last couple of months is we're seeing data, and I'm assuming my slides are still showing. We see this data, and we can show this data for Minnesota. We can show it for individual counties. We can show it for states, other states, the country as a whole, other countries, and it's still they're still relying on actual COVID positive tests from human beings. The disadvantage of this is with COVID, there's a large fraction of asymptomatic or very mildly symptomatic individuals who probably don't get tested, and so these are thought to be very much gross underestimations of the true COVID levels. The data I've seen is actually that about 10 times more people have been infected with COVID than have been confirmed to be positive with COVID. So that's the thought there is the sewage numbers are actually more reliable. At the same time, I've never seen any of that data in sort of the media. All I see it is with other people like me giving talks at conferences saying, hey, look at this great data I have. But so that's one of the frustrations is a lot of this work is being done and it's excellent work, but I don't think we're taking advantage of it very well.
I will say on Rachel Maddow last night, she had someone from, I forget what university it was in Boston, on their wastewater data for COVID. So I did hear a little bit about it, not from Minnesota, but from Massachusetts and the media last night.
What did the person look like?
Older college professor.
Okay, I probably know the person.
Yeah, you probably do. I don't recall his name, but he was with, I think, whatever university's in Boston, who was leading that research on there. Yeah, their Deer Island is where the wastewater treatment facility was, where they were measuring the COVID from.
Was it an Indian guy? That could have been a neat pinto.
No,
Okay.
it was not. He was, it was a white male, maybe in his mid-60s.
Okay.
Glasses.
Yeah, maybe I don't know who that is. There's the BioBot company, I think, is headquartered out of Boston. And they sort of invented this wastewater-based epidemiology concept, or they're trying to commercialize it. It's probably a better way of phrasing that. And you can do all sorts of things with wastewater-based epidemiology. You can look at, for example, methamphetamine use, and this leads into some of the stuff that Mark's been doing with his research as well. So, yeah, there's lots of people doing this. The stuff that I've seen has been most effective has been on college campuses, where they take the professors and then they go to individual like dormitories and buildings and get the sewage as it's leaving the building and do all their assays, and they can track COVID levels in real time. And there was a case at the University of Arizona, it might have been Arizona State, it was in Arizona, where they actually found positive cases in a dormitory, and nobody was symptomatic in the dorm. And then they went and tested everybody, found the 2 individuals who were positive but asymptomatic, and then isolated them to stop the spread, which was really effective. But it's encouraging that you've seen it on Rachel Maddow, so thank you. That makes me feel better.
Hey, Tim, I do have one quick question for you, a technical question, if you're still up for it, if you don't have to run right away.
Yeah.
I'm wondering if, going out again, if it might be interesting to look at antigenic tests side by side your genetic tests to see what you come up with. Or is it that the antigenic tests are just so much less sensitive that it wouldn't be worthwhile running? I mean, you wouldn't be seeing with an antigenic test whether or not something was a viable virus, but it might be interesting to see, well, are these, are the virus fragments anyway spreading hither and yon in ways that maybe the genetic material is not?
Yes, so that's a really interesting idea that I don't know how to respond to. So I'll tell you what, I'm going to think about that for the next week or two, in showers and at 3 a.m. That's a
Yes,
really good idea. So I got to think about that, but I don't have an immediate response to that. Sorry.
It might be that the antigen test is 2 or 3 orders of magnitude less sensitive anyway, and it wouldn't tell you whether or not that viable virus is present, just would alarm people. So
Yeah, definitely. And even with our positive tests, most people do not believe that the virus is viable in wastewater. It's just that we're able to quantify a fraction of RNA that is still there.
Right.
That's still a belief. That's not, there's weak evidence either direction at this point.
And it looks like we had just one more clarifying question. You were cutting out a little bit when you were talking about the negative test results of the swab. And they're just wondering if it was related to the test method.
Yeah, it's probably not related to the PCR step. A negative test is a negative test, and it can be negative for a number of different ways. My overwhelming logic, best educated guess is when you do a nasal swab and you test negative, and then 2 days later you get sick. The reason why that's a legitimate scientific negative, even though on a sort of a social definition, it feels like a false negative. The reason is you just don't have enough virus load in your nasal cavity to test positive. Okay. The analogy here is milk. You have yourself a bowl of Cheerios at midnight, and everything's great. You wake up the next morning and it's sour. Basically, critters tend to live and grow exponentially. And so a little bit of time can lead to a very massive bloom of the organism. So that's sort of what I was talking about there.
Great. Well, I know that you have to get going here to go teach a class, so we don't want to keep you any longer. We really appreciate you taking time out of your day to share your work with us. It's very interesting, and we look forward to, maybe hearing back from you after you do your second round of testing, maybe later in the winter. So thanks so much for joining us today. We really appreciate it.
All right. Thank you. Thank you, everybody.
Thanks much, Tim. That was great. Really interesting talk.
All right.
Thank you.
And then I think that our next water issues talk, we don't have anything scheduled because it'll be right over the holidays, but picking back up in January, we've got a full agenda through, I think, July. We've got talks scheduled for these bi-monthly water issues seminars. So we hope to see you guys all back.
Our next talk, let me jump in real quick, Brooke. January 14th, we have Susan Richardson from the University of South Carolina who's going to tell us about disinfection byproducts in water. That should be a really interesting talk as well. So hope everyone can join us for that.
Yep. So until we see you guys in 2021, I hope everybody has a safe and joyful, little holiday break here as we work through this interesting time. But I hope you all stay safe and happy and are able to find some things to pick you up if you're ever feeling down, and know that this water issues network is a good opportunity for you to come together with other staff. And if you guys ever want to just have an informal, let's just get together and talk, please let Mark or I know, and we'd be happy to, schedule an extra talk in there just to connect with everybody. So
yeah, absolutely. Well, what we try to do with this, of course, everyone, this is probably obvious enough, but what we try to do is reflect the interests of people out there who are listening.